Now, let me introduce Ilaria. She's presently assistant professor in the University of Foscari of Venice. And the most important thing is to say that she's a statistician. So she had the bachelor, the master, and the PhD in statistical school. And then she spent 3 years in Wallingford, in the Center for Ecology and Hydrology. And I think it was a very important period for us, at least, because maybe in these 3 years she was attracted by hydrology and hydrological processes. So I think I personally like such profiles when statisticians are attracted by hydrology, because I think it's a privilege for the hydrological community to have the contribution of mathematician and statistician. So in general, thanks, Ilaria, for this choice. And so I'm pretty sure that your talk will be very interesting. Today, you're going to talk about change in extremes, so detection and consequences. So the floor is yours. And,
Thank you.
And of course, don't be shy like with Simon. So you can write the question also during the talk, and I will collect and organize for Ilaria.
Thank you, Salvatore. I'll try to share my screen. While I do that, I will apologize slightly because Friday I had an accident. So if at one point I stop talking, it's probably because my bones are hurting and I need to go away. Sorry, I just need to, there we go. So hopefully you see my presentation. So luckily Simon actually already talked about some of the things I was going to talk about. But I think, as Simon said already, there is a lot of interest in the later years about change, in particular, in general, in natural hazards, and in many in water resources. And I particularly have studied the river flow and rainfall. Indeed, during my years at Wallingford, I was attracted to this topic and started working in hydrology. And I witnessed many studies that investigate changes in extreme rainfall and extreme flows. And then obviously their interest is partially, I think, also out of curiosity of understanding what's happening in the world. But I think from an engineering perspective, I suspect many of you are somehow have a degree in engineering. This is obviously important to understand how to manage infrastructure or how to build infrastructure, and if the relationship between frequency and magnitude of extreme event is changing, we need to worry about this. And I should say we also need to worry about things that become less frequent, also when extremes are becoming less frequent, because if that's the case, then we spend a lot of money maintaining infrastructures that are oversized. So a lot of people focus on the increase of extremes, but decreasing is also a problem. So is there a change? What could be causing change? So in this figure, you see here the increase in the urban cover in a watershed, in a catchment in the northwest of England. This is a figure I took from a paper we published a while ago, and I'll use this example a lot. Now, this is the case in which you have a very deterministic process that might have caused the change. Here, this catchment has, there was a small village, the small village of Leyland, which in 1970 covered a small portion of the catchment, and you see it increasing in time. And these percentages you see in each of the decades is this Urbext extent measure that is used in the UK to classify catchments as urban catchments. Another case in which you have a very deterministic cause of what might have caused change in the river flow behavior. This is annual maxima records in two different Spanish rivers, and that red line that you see is a reservoir index that as the name says, gives an indication of presence of reservoirs. And you see that the catchment on the right, which has experienced a big increase in reservoirs, as a very clear evidence of changes in the flow behavior. But I think in many, many studies that we see, there is an implicit assumption, an untalked about assumption, which is that climate change is driving changes in the hydrological processes. And obviously, I don't even want to get into the discussion of whether this is man-made or not, but I think there is, just looking at this graph, this is temperature anomalies for the global temperatures. It's pretty obvious that things have been changing. And in some sense, it even doesn't matter if it's man-made or not, man-made or not. The only thing that matters is, as Simon pointed out, is whether we can forecast whether this will continue to increase and whether we can somehow understand how these changes in temperature might affect a variable of interest, for example, extreme rainfall or extreme river flow. But I think this is an implicit assumption in a lot of studies that look at change, and I think we should just be very honest about what are our assumption of the causal links that we assume. If there is reason to believe that increased temperatures increase the convective potential and therefore increase rainfalls and therefore increase number of floods, we should say that so and not just blame it on time, because time is not a very useful explanatory variable. So why should we study change? As I said, possibly because we are interested in understanding how things are changing and how external drivers like temperature and land use might affect a process of interest. But we also might want to do this because we actually want to compute risk, and not me, as I'm a statistician, so I don't want to maintain infrastructures, but engineers who might want to quantify risk to calculate the risk connected to some infrastructure, then we need to know whether this is changing, of course. And I think one important thing to keep in mind is that the methods we might want to use to do these things are different. We might need to use different methods depending on what is our final goal. And I'll try to show some example of that. And these different type of questions we might have are sort of classified in the literature as the detection, in which you just detect that there is an effect. This is interesting, but not very interesting, because we just know something is changing, but we don't know why or how. And sort of we don't really know what to do with this information. And there is the quest of attribution, so really saying, well, I have a certain process X which changes my process of interest Y, and I attribute so much of the change of Y to this process X. And then I think the last question, which I know less about and I want to read more about, but I think is also less discussed in the literature, is what do we do with this? Where do we go from here? If we have detected a change, how do we design new infrastructures? And in my job at CH and afterwards, I was dealing quite a bit with decision makers, with the Environment Agency in the UK. And really, this is what they're really interested in. That first catchment we saw in the northwest of England has been flooded 4 times in the last 20 years. And obviously, the citizens of that city would like the authorities to, get their understand how possibly climate change or whatever it is that is changing their risk. So talking of that northwestern catchment, this is the data for that catchment. This is annual maximum flow. This is the only data set that we have available. And luckily, as you might notice, the data set ends in 2007, I think. So we don't have the largest, biggest floods of the later years. But you can already see here, in the left, you have the annual maxima as a function of time. And you see that the biggest event happened far in the past, but then you have an increase as of 1985, the flow magnitudes have been increasing very clearly. On the right-hand side, you have exactly the same data set, but just with a slightly different way of presenting it. And this is just to sort of show how different data presentation can show different aspects of the data. And this is something I hope we can discuss more next year. So is this data changing? Well, and maybe yes, but we know something more about this catchment. We know from the rich data set of the National River Flow Archive in the UK, we can derive the catchment average rainfall for this data set, for this catchment. And here you have the average rainfall in all the years, and related to this is simply a scatter plot of the average rainfall and the annual maximum flow of that year. And you can clearly see that years which were fairly wet are characterized by fairly large maximum annual flows. This is because most of the flows in the northwest of England are winter events in which a big rainfall event on wet soils causes flooding or large flows. On the right-hand side, you have how the urban extent relates to flow maxima, and this is nothing but a linear transformation of time, because this is a place where urbanization has only increased. So you should see that the changes in land use are maybe related. So here is the years with more concrete on the ground, and you see that there seemed to be a change there. Now, interesting to see, this is this big event that happened in the early years. So in years with low urbanization, also happened in a year with a big rainfall, a large rainfall, okay, large annual rainfalls. So we can sort of expect that we can explain the presence of this large event, even if it's in a year with low urbanization, by the fact that you have high rainfall. So this is the data that we receive. Now, before we can actually say anything about whether these relationships mean anything from, is there a change in the data? We need to make some, need to abstract a bit and think about what is the statistical framework we might want to use. So we need to assume that the sample that we have, that these 33 data points that we have observed are a random sample from the population, from a population. This is the first assumption that is absolutely not true in hydrology. We have an opportunistic sample. We don't have a random sample. We only take whatever is measured on that year. But we pretend that this is true, and we assume that we have a random sample, and we're interested in using this to learn something about the population. Today, I will only discuss about parametric methods, but maybe next year, hopefully, we'll discuss a bit about non-parametric methods. What do we mean by parametric methods? Well, the idea is that we assume that this sample follows a certain distribution, which is parametrized by some parameters, theta. And then once we know what the value of these parameters are, we know everything about the distribution. And the parametric framework has a big advantage, because especially when we want to understand change, it allows us to describe change in a very clear way. It's very easy to write down models of change, and it's easy to extend to pretty complex method. What is the idea? As I said, we assume that each member of the sample comes from a certain distribution. Typically, we assume that the distributions are IID, so independent and identically distributed. This is another assumption that is probably not true in hydrology. We then assume that this distribution is parametrized by theta, and then once we find a sample, an estimate of theta based on the sample, we know everything about the distribution. And we can use different estimation procedures, and I'll mostly use maximum likelihood, which is maybe the queen of estimation procedures. Arguably, Bayesian approaches are the king of estimation procedures, and can actually overcome many of the problems that Simon highlighted, in my opinion. But they come with the drawback of Bayesian approaches is that they are more complex and more time consuming. Just very quickly, the only thing I want to say about the maximum likelihood estimation for today is that the reason why it is the queen of estimation methods is that it asymptotically, what we have is that the maximum likelihood estimates are unbiased, and we can derive their asymptotic distribution. So it's very easy to quantify uncertainty in the parameters when using maximum likelihood. So how do we parameterize models so that we can describe change? So we assume that the distribution is, instead of being fixed for each one of the y, we assume that each one of the yi's follows a distribution which is parameterized by theta I. Okay, so for each year of the observation, we assume that the thetas are changing, and then we relate some variable of interest, for example, the urban extent, to the values of the distribution parameters via some link function g of xi. And so from this, we can then write that yi, which is nothing but y given x equal xi, is a distribution which follows this structure with g of xi being theta. Now, the easiest model you can do with this to characterize change is obviously, for example, linear regression. The least square method is nothing but the maximum likelihood estimator for a normal distribution. And indeed, once you characterize the distribution mu I, and so once you characterize yi as being a distribution with mu I changing as a function of some covariates, for example, urban extent or rainfall, then once you know what the value of mu I is, and you have assumed that sigma is constant, and you estimate sigma, once you've characterized these two parameters, you know everything about the distribution. So this is just very quickly, you can write down the likelihood for the normal model, obtain estimates, and then, for example, if you want to test whether the certain parameter beta I is significant, so is different from 0, for example, well, you rely on the normal distribution of the maximum likelihood estimate to do that. One thing I want to say is, I think there is because of the software output, the default in the software is that you test whether beta is equal to 0. That's what you always see in papers, not only in hydrology papers, any papers. But really, there is the idea that we know that betas are not equal to 0. Like no value, we know that the value of the slope is not really of interest. What we want to know is whether there is a change that is big enough for us to take action. And this is something I tried to mention in this paper that I think nobody really picked. So I want to re-emphasize, we can change the default. We do not need to test for beta 1 being equal to 0. You can test for different values. You can test whether your slope, whether your change is larger than 0.8 or anything like that. Okay, so just like we did for the normal model, once you decide what is your distribution you believe to be the good one to represent your extremes, then you can just use the same framework and assume that theta I changes as a function of your covariates with some link functions, and then your yi is nothing but y given x equal to xi with changing parameters. As Simon mentioned, there is some theoretical results which might be useful to think about what are sensible distributions for the extremes. And I think here is a place where it would be interesting to talk more. Hopefully we can talk a bit more about this next year. There is a big discordance between what statisticians use. So statisticians always use the GEV distributions, while hydrologists are, I think, on a quest for what is the best distribution to use for extremes. And this causes a bit of tension, because essentially most of the results in the statistics literature are not very useful for hydrology, and that's a bit annoying. But so what is an extreme, really? There are two typical ways in which the extremes are described in the extreme value theory literature. So you can think of an extreme as something that is the largest event over a certain amount of time. For example, you can think of annual maxima, right? So you take all the records in a year and you take the largest event in the water year, or you can think of events which are above a high threshold. And I'll go really quickly about these classical extreme value theory results, just to present some potential models and show some challenges connected to this. This is a bit basic extreme value, and hopefully next year we can talk a bit more about other interesting things. So traditionally, there are these theoretical asymptotic results, which are based on the assumption that we observe a stationary stochastic process. So we observe the outcome of a stationary stochastic process. This is another assumption that is definitely not true for water hydroclimatological data, but we disregard that and we pretend that it's all good. And if we had maxima of a stationary series, you can show that asymptotically the limiting distribution of maxima would be the generalized extreme value distribution, which has 3 parameters, while when you consider extremes to be all the events above a certain threshold, then you can show that the limiting distribution would be the generalized Pareto when it comes to the magnitude of the events, and then the typical distribution taken to describe the frequency of the threshold exceedances is a Poisson distribution, and then to actually make estimations about the frequencies of large events, you need to combine these 2 information. And this process works very well when things are not changing, but sort of breaks down a bit when you want to model change. So this is what the GeV distribution looks like. I guess many of you have seen it. I'm just leaving it there for for posterity. It has 3 parameters: allocation, scale, and shape parameter. And I think I want to highlight, this is one of the most annoying thing that happened when I moved to indeed the Center for Ecology and Hydrology, was that I realized that hydrologists and statisticians use a different way of writing the GeV. So just make sure when you use software that you know which GeV you are using. Also, they use different Greek letters to indicate the same parameters. Very annoying. This is the quantile function, and I want to spend a minute on this. What you see here is that the quantile function is nothing but, so this is the location parameter. So this is for the case with psi equal to different from 0. So the Frechet or the variable. But the quantile function is the mu parameter plus some transformation of the scale and the shape parameter, and then something that has to do with the probability of exceedance and the shape parameter. And this is interesting because when the first model that you always see when you want to model change is a linear model in the location parameter. And if you think about it, this means, and I'll show you that later, that that what is changing is that the quantile function, it becomes a linear function of the location parameter, but this component sort of stays constant. And I think this is something I'm currently working on, so I'm not ready to present it really. I want to study a bit more. I want to understand a bit more what is the consequence of the different model assumptions we make on the description of change. So finally, we go back to the data. This is that catchment in the northwest of England. We are just fitted some different models of change in the location parameter. And here I'm using 3 different distributions to test whether there has been, and here I'm using just change in time, any type of change, to see whether we can detect any change. And you see here the median and the 50-year event, the effective 50-year event as these lines, while the straight lines are the case of no change. So the estimates for no change. I want to just show what the estimate is using 3 different distribution functions, because what you might notice is that here in the median, okay, you see that the estimated effect of time is very similar. It's the GeV and the GLO line. Oh, I'm using the GLO, sorry, I'm using the GeV because that's the theoretically correct distribution. The GLO, the Generalized Logistic Distribution, is the distribution that is recommended in the UK for peak flow data. And the log normal distribution is just a very general, very sort of easy to fit distribution. So, and it has the property that the skewness is, well, it doesn't have its own skewness parameter. So you can see that for the log normal here, it always estimates a much lower value the 50-year event, because indeed it doesn't describe the higher end tail very well. But in some sense, if you're only interested in whether you want to detect a change, it sort of doesn't really matter which distribution you use. You will get a similar answer. But if you actually are interested in estimating the higher end quantiles, the choice of distribution that you do has a big impact on your understanding of what is the actual value of the upper end quantile. And this is problematic because the moment you start adding lots of parameters to describe change, the more you add variability to the system, and it becomes harder and harder to understand which one is the correct distribution to use. So there is a tension between, there is a tension in choosing the correct distribution. Okay, so this is just how the model looks like when you use the urban extent rather than time as your explanatory variable. Still a significant effect. This is what happens when you include rainfall as your explanatory variable. You see that there is a strong effect of rainfall on the annual maximum flow for the catchment, because obviously time, the reason why I want to avoid using time is that time is a pretty useless explanatory variable. Also, it only goes in one direction. We know where time is going to go. And this is what happens when you have both urban extent and rainfall in your model. And you see here the straight line, the lighter line is the relationship of mean rainfall for a given median value of the urban extent, while the line that goes up and down is the actual estimate from year to year. Okay, but sorted by rainfall. So you see that the different years with the different urban extent will have a different estimated median. So that 2-year event changes from year to year. This is the same picture, but with urban extent given different values of the main rainfall. And what you sort of can see is that the mean rainfall has a very strong signal, and the urban extent makes it vary a little bit around. The urban extent has some signal, but the rainfall makes it change quite a lot around the regression line. And this indeed can be perceived also when you look at the magnitudes of the coefficients for the GEV location parameter estimates and their uncertainty. For when you look at the rainfall, the parameter for the rainfall, it's fairly strong and very, very significant. The parameter for the urban extent is significant, but just about. For those of you who know how to do maximum likelihood estimator quick calculations in your head about whether things are significant or not, this might make sense. Otherwise, we'll discuss how to interpret these tables next year a bit more in detail. But today we don't have time. An important thing to say is that, so what I get from this table is that you can see if you include rainfall, it explains a lot of the variability of the annual maximum rainfall. That's nice. If you include urbanization as an explanatory variable, it explains a lot of the variability in the data. But you explain even more variability in the data when you include both the variables. And this sort of means that the change that you can attribute to urbanization is really the one that is brought by the change in land use rather than rainfall. Because if you just fit a model in which you include the urbanization, you sort of don't know that the changes that you observe in the river flow might not be due to rainfall changes, which you are not including in the model. So by including rainfall, which is arguably one of the main drivers of flooding, we sort of take out the variability that is due to a natural process, and that's rainfall. And then on top of that, we still find that urbanization has an effect. There is a drawback of this. Because urbanization is monotonic in time, what might be happening is that there is something else that has an effect that is monotonic in time, and that urbanization is explaining this unknown factor. But, well, in the paper, we try to overcome this, and in some sense, well, there is so much we can do with the data that we're given, really. But what we did check for is that urbanization and rainfall are not correlated to each other. So rainfall has not been changing in time. And by consequence, in their urbanization extent. The big drawback of this study, and I think a lot of studies, and I think this is another thing that we should try to overcome, hopefully in the future, is that using linear models is really a non-nice. It's way too little. We should be using more complex model. Linear relationships are not how natural systems evolve. Reality is complex, but we need to use linear systems, linear representations of change, because really with 33 years of data, fitting anything that is not linear is going to be a bit optimistic. Now, very quickly, I just want to say this is the other type of representation of extremes you could have, in which you have change, in which you have points which are above a certain threshold. So all these red points are intended to be extreme. And then the classical framework tells us that we can model the magnitude of these extremes, of these exceedances, as generalized Paretos. And the generalized Pareto is parameterized by two parameters, because the location parameter it's a bit what Simon had said. There is a threshold, there is a lower bound, which is not a parameter, it's a constant, is chosen a priori, and that takes the role of the location parameter for the distribution. This means that the most typical models of change, when you see people modeling generalized Pareto distributions, is modeling the sigma parameter as changing, because the location, the threshold is given and is kept fixed. This can be arranged, but then this means that this part of the quantile function is changing rather than this part. So you're modeling a very different type of change in the quantile function. And indeed, there is a nice framework that allows us to use point process representation of extremes, in which we use the same parameterization of the GEV distribution, but on peaks over threshold. And we'll talk a bit more hopefully next year about this, but the idea is that we model the number of exceedances as a Poisson process, and then we describe the intensity of the Poisson process, so of the number of events, as something that has to do with the magnitude of the events, which makes sense, because years which will have lots of records probably are years in which river flows were high. And therefore you can then model this Poisson distribution as a function of the GEV parameters, and then we can describe changes in the point process, in the peaks over threshold, using the GEV parameters. And this representation is severely underutilized, I think, in hydrology, and it's explained very easily in the Cole's book and in the papers of Rich Katz, which I have links at the end. Okay, so we do this and we use this parameterization, and this is the change you see in time. I only have the slide for time just to show you this is the median, the estimated median as a function of time. When using the peaks over threshold data with a point process representation, you get a significant change in time. And indeed, when you compare the estimated parameters, they have similar values and definitely similar order of magnitudes and of significance. The thing that changes quite a bit is the shape parameter here. But really what changes is it's the estimated value, but mostly also the uncertainty. So the other thing to notice is that when we use the point process representation, we have a lot less uncertainty in the estimates, and from a statistical point of view. And this is due to the fact that we have a larger sample size, just because we have taken more than one event per year. We have taken 3 events per year, I think. Now, whether reducing our statistical uncertainty is a good thing, that's to be seen, in the sense that all of these uncertainties are measured, are computed based on a number of assumptions, which, as I have tried to mention, might not be true. So parametric approaches are easy way to include changes in a distribution by means of the parameters. So it's very easy to do this, and this might be a bug and not a feature, in the sense that it might be too easy. It's so easy to just download the R package and fit 1 million of distributions with 1 million of parameters changing, without really thinking what is the implicit and explicit assumptions we're making about processes and what influences our Y. And And yes, one of the things that I see as a reviewer that infuriates me is not only trying a lot of different distributions, but saying that you will investigate how things are changing in time, but then doing the goodness of fit on the original data. Now, if you have taken a course in statistics, you have learned that you need to check the normality of your residuals on the residuals, not on the original data. So you should do this also for extreme value distribution. If you think that your marginal is changing, fit the change first and then check what is the goodness of fit measure on the residuals. And there is a challenge with the fact that extreme value theory and practice are not really aligned. Detection is hard, and I'll try to speed up, but really we have the problem that we don't observe a lot of data, so we don't observe all the parts of the process we're interested in. If you think about the mean annual rainfall that I have observed in that catchment, it's not very variable. I'm sure if we could observe 200 years, we observe a lot more variability in our explanatory variable and could explain better how X influences Y. But we don't observe that. In most cases, we have 40 years of data, and it's hard to believe that we are observing the whole range of possible values of our explanatory variables. And it's hard to identify complex systems because we don't have a lot of signal. And if we are detecting change, what are we detecting? This is an excellent opinion piece I recommend reading. Attribution, statisticians do work on causality, but the best we came up with is clinical randomized trials, which is impossible to do in observational data like environmental data. Now, climate scientists, of course, have sort of come up with the idea of running gigantic models under natural pre-industrial conditions and after industrial conditions, and then we could do this a bit more in hydrology. But I think that the problem of causality is it's coming up with a good framework for causal inference in environmental data is a challenge. And also there is the problem that there are feedbacks in the systems. So urbanization impacts the climate, which in itself impacts river flow. This is a nice paper that shows this type of feedbacks. And I don't have time to really talk about this. All I want to say is that once we include, this is just to show that the confidence interval for the 50-year event, the 100-year event, in annual maxima, when we have no change in the estimate, or when we do explain the variability with rainfall, that the width of the interval increases when we introduce a variable. The variable explains the variability in the data, but there is so much uncertainty about higher end quantiles that including an additional variable in the data makes things more variable. And again, this is something I hope to discuss more next year. How is it worth it? How do we use the information that things are changing for the estimation of higher end quantiles? And I think, well, I'll shut up and just say the last thing I want to say, which is next year you hopefully can expect me to present everything that I do in the most reproducible possible way. And by this I mean there is a gigantic problem in science about the reproducibility crisis, and it's becoming easier and easier really in R or Python to do science that is sort of easy to be transparent about. So this is, if you follow the link on the slides or look at that, you can see that all I've done today, all I've presented today is presented here as a file. When you open it, you will see this file, which mixes R code and LaTeX and just a text. And then in those slides, you have all my analysis. You will see perfectly, you can derive exactly what I've done, how I've done it, and you can then check whether I lied to you about anything I've said. I think I'll stop here, Salvatore.
So thank you, Ilaria.
Already late.
Very, very nice presentation. Really inspiring. I think next year will be the opportunity to work on it during summer school. So okay, I have just a question from Marco. So this time I think, Marco, you have the floor.
Yep. Thank you, Ilaria. I really enjoyed it. A lot of things that I can relate to, and I have a question, very broad, meaning you pointed out some limitations, very basic limitations about the way people do things. Also, goodness of fit, etc. But there are some hypotheses at the basis of those methods, classical methods you mentioned. Do you think these are important limitations, meaning the Poissonity, the Poisson nature, the independence? I mean, how do you think that is limiting the ability of those models to capture reality?
So I think I think there is no doubts that the assumptions are not completely fulfilled. Of course, one option is to use the metastatistical extreme value distribution. One might say no, but which is what Marco has been working a lot on. No, I think it would be interesting actually to test this a bit more. One option is also to model the, so to include additional parameters to model the fact that we know that our observations don't match the hypothesis. But I also see a lot of papers in which they say, well, because the POT need to be Poisson, I'll decide on the threshold value when the goodness of fit says that the data are Poisson, which is sort of reverse engineering things. You should have a threshold which is what you want. And then if the data are over dispersed, then you need to assume that things are negative binomial, and then you need to reinvent theory in which things are negative binomial instead of Poisson. But I think it's not entirely understood how much it influences the final results. At least not that I'm aware of.
Thank you.
Okay, we have the second question, and maybe the last is from Richard. Richard?
Okay, yes, can you hear me?
Yes.
So I'll be cutting into my own time. I couldn't resist to say three things. And then we can discuss later. Wonderful talk. As you know, Ilaria, I love all your work and follow it closely. But when you tell me...
Likewise.
But because of your being a statistician, and I'm a hydrologist, we have a slightly different viewpoint of some things. First of all, on regression, it's true that fitting a linear model is almost always nonsense, but linear regression using a Tukey transformation can be used to fit the most complex nonlinear models. So let's not rule out linear regression just because it's not being used properly. Number two, I don't think it's even possible for a natural process to have a change in the mean without a change of some kind in its variance. In fact, when we looked recently at the coefficient of variation of annual max series, we find almost very, very few cases where the coefficient of variation appears to be changing. So it may be useful as a first order approximation to assume a constant CV, but a changing mean. And the third thing I'll say is when we talk about the partial duration series versus annual maximum, it goes back, there's a long history in the hydrology literature from the 70s and 80s, in particular some people like Eric Wood and Dan Rosberg and Jerry Stedinger, and there is a rule of thumb that comes out of those papers that were very rigorous Monte Carlo experiments that showed that if you have less than about, if the truncation level of the partial duration series is less than about, yields less than about 1.6 events per year, you'll always be better using the annual max. It's only when there are enough significant events in a year that it matters to use that a POT series, in other words, looking at the variance of the quantiles. Anyway, I just referenced that we all, and I often do the same, I forget that there is a long literature and history in hydrology, and we're very evolved. That's all I wanted to say. Those are just points of clarification.
Yes, they're all incredibly correct and things I couldn't really fit into this quick talk. But yes, no, there is a lot of literature on the POT versus amax, and regarding the coefficient of variation, I totally agree with you. Reviewer 2 doesn't, but I have something coming up about exactly that. So I am hoping to be able. I'm happy to share the paper with you if you would like. I think we will.
Yes. We have lots of this.
But yes, I that is one of, so just very quickly, because I didn't, I tried to put too much. But I think one of the big, you see it here. So a lot of people just fit the location as a changing function, but this implies that that the difference in quantiles is just this function. So it doesn't. It's a constant for different return periods. But this being a constant means that, relatively speaking, the change in the median is larger than the change in the 100-year event if mu1 is positive, which is not what you would want to know as an engineer, I think. You don't want your median to increase and not your 100-year event.
Yes.
So I'm trying to make this, we can talk offline.
Later, during coffee break.
Yes, we'll talk during coffee break.
Okay, so I think that thank you, Ilaria, again.
Thank you all.